Hi everyone, welcome to NMC 113. Today we'll actually be looking at chapter 4. Chapter 4 we'll be looking at this moment point defects, and the point defects that you find mostly which are common are vacancies, right? Vacancies, and you also have self interstitials. Now, theoretically, you may suppose that a perfect material exists, but meteorologically speaking, that's not possible. There's no material or metal that does not have defects. You'll always find vacancies in metals. They're not absolutely perfect. So you find that you have certain defects, point defects, as stated above. And you can see from the sketch, vacancies basically a void that has been left where an atom is supposed to be. It's just a void and there's no atom. Self-interstitial is actually an overcrowding of a specific area by a group of atoms, and that's basically it. And then there's a dependency on the number of equilibrium vacancies on temperature, and it's represented according to this relationship, which you'll just see in your notes or your textbook. Number of vacancies, that's N, and you have N. Okay, a number of vacancies, NV, and then N is the number of available sites, right? And then you have this Arrhenius equation of the dependency of number of vacancies. This is activation energy required for the formation or the initiation of vacancies. And then you have Boltzmann's constant K, right, and temperature in kelvins. So the relationship is actually shown in the dependency of vacancies on temperature. And now you also need to be able to determine the number of possible sites, right? So that's N, which is can be calculated as Avogadro's constant multiplied by density over atomic weight. Mostly this is the units for this. It's number of atoms or sites, right? Number of sites per volume. Now when we're saying that number of sites, we're actually even counting the number of sites that are occupied by the atoms. Do you understand? So we are looking at the entire structure or the entire spectrum of the structure. We are calculating how many possible sites are there. So even the sites that are occupied by atoms, they are still possible sites. That's what we're talking about when we're saying that number of possible sites. So that's actually the equation you need to actually know. Sometimes they would ask you to calculate the concentration, vacancy concentration, right? Vacancy, concentration. That's just NV over N, right? That's the vacancy concentration. So you don't actually need to do anything extraordinary about this. We'll do examples, like I said in some of the videos, that here we're just discussing the concepts. So yeah, I think you know, if I say anything more than this, I'll actually be exaggerating, but that's actually it on point defects. Vacancies are actually the most important, but there's quite a lot of theory in chapter 4, so I think that this video, there isn't gonna be a lot of content, because obviously I'm not gonna cover like theoretical concepts which I deem to be, something that you could read yourself, and it's basically just reading the concepts, and after you read the stuff, you'd understand. Like, there isn't anything remotely challenging about those particular concepts, because they're also line defects. You need to actually also understand the concept of dislocations, right? Where dislocations are a form of a line defect, where it makes it possible for deformation to take place. That's why materials deform plastically, especially when we're talking about in the context of metals. They can deform plastically because of the movement of the dislocations. Whether these dislocations are jumping or gliding, they actually allow the possibility of permanent deformation. And you also have impurities in solids, right? I'm only talking here because I know that this is like it's just theory, and if you read through it, you'll know. And with solid solution and interstitial atoms, for solid solution, you need to actually familiarize yourself with the Hume-Rothery rules, and those are outlined perfectly in your notes or in your textbook. So I'm not really gonna write those things down, because it's really a theory that you have to go through. I don't need to, try and facilitate that. That's something you should personally take it upon yourself to do. Besides that, I think we can actually move forward, because there's another section which probably contains quite a number of calculations. That's the concept of grain size measurement. So when it comes to grain size measurement, the idea is when you're doing what is called metallography. That's usually when you analyze samples at a microscopic level using a microscope. You find that now you're dealing with certain levels of magnification, and you'll probably be going to be looking at the grains, the size of the grains, the grain boundaries, because those virtually are important, because they contribute a lot in material properties. So this concept of grain size measurement is establishing foundational work to concepts like metallography. That's experimental work. So we have the ASTM method for grain size measurement, right? ASTM method, which is according to this equation, N magnification over 100 squared equals to 2g minus 1. So this is the ASTM method, and let me just identify all the components within the equation. And the definition of each and every component in this equation is important, because I mean you're gonna be evaluated based on your understanding of these. So questions will come out in such a way that it requires you to have an understanding. So n is the number of grains, right? Number of grains per square inch. Per square inch, and then m is the magnification, right? And g is the ASTM grain size number. Pay attention to this. This is not grain size, right? It's grain size number. It's a unitless number, so don't get confused. Grain size number and a grain size is actually, those are totally two different things. And what you must understand from this is that the relationship between g, which is the grain size number, and the grain size, there's an inverse proportionality relationship, right, between those two. But we'll discuss this shortly. But you must just know that the grain size number and the grain size are inversely proportional to each other. So it means that the higher grain size number you have, the smaller the grains. Do you see that? So usually you'd actually have, if you look at the drawing on your left, you'll see that you have a specific number of grains within, a particular micrograph, and this micrograph has a diameter. So the grains at the periphery, these grains at the periphery, the ones that span the circumference, all the grains spanning the circumference, all of them, they're considered to be half grains, right? So it means that when you're going to be counting the number of grains, these ones at the periphery here, or on that are spanning the circumference, will be considered as half grains. So you count all of them, and then let's say you have an x number of them, so it would be half multiplied by x, whichever number of these grains are, plus the ones on the inside. You count how many there are. Let's say it's hypothetically it's a y number of grains. So this will actually help you to get the number of grains in counting. And sometimes you get a question where you'd have to measure this this diameter, right, to actually get the area within which you find all these grains. Remember, the grain size number is number of grains per square inch, so it means that it's actually the number of grains per an area, right? You just need to actually know the conversion between inch to centimeters or inch to millimeters, and you must actually be familiar with those conversions, because they will actually come into play. So yeah, that's really basically it. There's virtually nothing special beyond this point. that I can actually mention. Now let's go back to what I said would discuss, which is this, that the fact that the relationship between the grain size number and the grain size, there's an inverse proportionality, and this is actually in your notes. I took the liberty of copying this from your notes. This picture, see, you have fine grains, and then you see that here the grain size number is 10, and then when you go around the grain size, right, the size of the grains are getting smaller, and they're getting bigger and bigger, and the grain size number is becoming smaller and smaller. And you see here with very large grains, you have a grain size number of 1. Now, what constitutes this? Like you'll see, like according to this relationship, and let me just write it again. Let me just write the standard formula at a 100, magnification of 100, right? Assuming the magnification is 100, so you just have n equals to 2 to the power of g minus 1. So you'll actually see that according to the definition of n, which is the number of grains, right? The number of grains per area. Say let's assume that all the areas here for these specific grain, area number, let's call this one area number 1, say this is 2, this is 3, area 3. Now you'll see that within the same area you have a lot of grains, right? So it means that this one would actually have more grains per area. Do you see that? And according to this equation, you can see that when you have more grains per area, it is going to increase with the value of n. Does that make sense? I hope that actually makes sense. I'm even asking, but there's no way you'll respond to me at this present moment. So now that constitutes the grain size being inversely proportional to the grain size number. That's why it actually is, in fact, the way that it is. But I hope you understand that relationship, because sometimes a theoretical question can be asked to test your understanding on these. We're going to move on to the linear intercept method. Right, this method is actually used to measure the mean intercept grain size, basically stated as GS, which is equals to this LT, right? P multiplied by M, which is the magnification. Let me just identify all these parameters. LT is the total length of all the lines. Right, drawn on the micrograph. So it means that these red lines, you're actually going to measure. Let's say this is line 1, this is line 2, this is line 3, etc. Right? You count all. Okay, and then after that you measure. It will actually be the sum of all the lines. Do you understand? So you're gonna measure the length of each line and then you add them together, meaning it's gonna be L1 plus L2 plus L3 and so on. So it's the total length of the lines drawn on the micrograph. And then P is the total number of grain boundaries, right? Grain boundaries crossed by the lines. Right. So for example, let's look at L1. You have the line crossing this grain boundary. That's 1, 2, 3, 4, 5, 6, 7, 8. So L1 is crossing 8 grain boundaries. Do you see that? And then you're also gonna count how many grain boundaries L2. You know, so it means that the grain boundaries, for example, is a sum. Okay, so P1 would actually be the grain boundaries crossed by L1, for example, and then after that you do the same for each line, and then you add them together, and then you'll get the total number of grain boundaries crossed by the lines. Right, hopefully that makes sense. And then M, as you know, it is the magnification. And then that's it. And the units for L, L stroke, or the mean intercept grain size, it's usually micrometers, right? That's actually the standard unit. So yeah, if you're given a problem where they're asking you to use the linear intercept method, this is basically what you do. That's it. I'll see you on the next video, which will actually be chapter 5. You may be feeling being hard done by on chapter 4, but like I said, there's a lot of theory, and it's things you should be reading, right? It's not really complex things to deal with.